Hello everyone and welcome back to this next lecture in the machines lecture series, and this is where we had left off last time, where we had concluded that for a squirrel cage induction motor, which is a cylindrical rotor induction motor, we found that the self-inductance of the rotor was also independent of theta m. So in the case of a squirrel cage induction motor, or for that matter any cylindrical motor, the self-inductance of the stator and the self-inductance of the rotor are independent of the rotor position angle, right? So now, just to complete the discussion, we had also compared what happens with a salient pole rotor. And in the case of a salient pole rotor, we found that the self-inductance of the stator was dependent on the rotor position angle. So this independence no longer holds for a salient pole rotor. So the self-inductance in the case of a salient pole rotor is a function of the rotor position angle. Now, in this lecture, we are going to look at what happens with the self-inductance of the rotor in the case of a salient pole rotor. Even though the immediate discussion is not on salient pole rotors, but instead on cylindrical rotors, for the sake of completing the discussion, it's worth having this one look at. So, as before I start the lecture, a little bit of brief background that if you're interested in these kind of video lectures, but you would like something a little more comprehensive, I do have full-length online courses that you can access on my own website, which is pythonpowerelectronics.com. So this is the home page of my project, and in this, if you click on the button Learn, it will take you to the list of courses. So this is currently the list of courses which I have right now, which are 5 courses. The very first course is Simulating Power Electronic Circuits using Python, and in this I talk about the basics of how you can use Python and Python Power Electronics to simulate power electronic circuits. The second course I have is called Basics of Digital Signal Processing for Power Engineers, and in this I talk about how you can use Python and packages such as the signal package within SciPy to analyze and design filters for power engineering applications. The third course I have is Simulation of Magnetics for Power Electronics using Python, and in this I talk about how you can use Python and Python Power Electronics to simulate magnetic components such as inductors, coupled inductors, and transformers. The fourth course I have is called Control Analysis with Python for Grid Connected Converters, and in this I talk about how you can use Python and packages such as Python Control Package to analyze and design controllers for power engineering applications with the specific case of a single phase inverter connected to a single phase grid. And the last course I have is called Why Specialize in Power Electronics, and this is a free course targeted towards either high school students or junior undergraduate students to tell them about some of the opportunities and challenges available in power electronics so that they could choose power electronics as their specialization. So all these courses are available on 2 platforms, which is Decibels Labs and Udemy, and if you click on any of these buttons, it will take you to the link for the course. The link for this page is available in the description of this video, so if you're interested, please do check out the description of this video. With this, I'll return back to the lecture. So once again, the idea here is to determine for a salient pole induction motor or a salient pole rotor or induction motor with a salient pole rotor, how would be the self-inductance of the rotor as a function of the rotor position angle. Now, given the fact that the stator inductance is a function of the rotor position angle, one would be quick to jump at the conclusion that the rotor inductance will also be a function of this rotor position angle. But before we jump to this conclusion, it's always a good idea to go back to the flux diagram, draw the flux diagram, and actually try to figure it out. So let's go back to the flux diagram, which is here, and this is what we have drawn for the salient pole rotor. So this is the salient pole rotor, where you can see there are distinct poles rather than an actual cylinder. And in this case, we found that because of this salient pole structure, the position of the rotor does impact the flux produced by the stator. And since the position of the rotor impacts the flux produced by the stator, therefore the self-inductance of the stator is a function of the rotor position angle. Right? And we can see this. For example, if we rotate this, we will see that in this direction, the flux is the weakest because the air gap is the smallest when this salient pole, only in the area covered by the salient pole, and in all other positions, in all other places, the air gap is the largest. In comparison, if this rotor were to be rotated by 90 degrees, we see that it's totally different. Now in this case, since the rotor position is in the horizontal direction, the flux produced by the stator now will have a much lower, or rather flux produced by the stator will be much stronger, for the simple reason that now the air gap, or rather the path for which this stator flux can flow, is now much stronger or much smaller. Because now, for example, if you see that the flux produced by the stator can now flow in this direction in a much more uninhibited manner. So therefore, the rotor position angle does decide how strong the stator flux is. So now let me just go back, and to continue this, we have to now copy this diagram. So let me just go and select it. So I will copy this. First I need to move it. So let me just move it up. Paste it. I think I have a little more space, so let me move it down. So we now have a copy. So in this copy, I'm going to delete all these flux lines, which were the stator flux lines, because we are not looking at the stator flux anymore. We are now going to look at the rotor flux. So I'm going to delete all of these, and we will leave the stator coils as it is. And here we have the rotor, we have the stator, and this axis is basically the axis of the stator, which I'll leave it as it is, and this horizontal line can also be as it is, because we need a horizontal reference anyway. Now the question is, how are we going to look at the rotor coil? In the case of a cylindrical rotor, we had mimicked something very similar to this. So we said that we can consider two rotor slots diametrically opposite each other. In the case of a salient pole rotor, we have to now think, how do we wind the rotor such so as to produce a flux? Now, if we consider such a rotor, that is a salient pole rotor, we would like to wind the rotor coil in such a way that it produces a flux that passes through the rotor. Alright, so we can think of various ways. For example, we can say that there could be, let's say, one coil here and another slot here, right? And we can consider another slot here as well as here. So the actual way of winding may be very different, doesn't really matter. But what is important is, let us say that we had wound the coil in both of these. So for example, we were winding a coil through these slots and we were winding a coil through these slots. And of course, we can also take these conductors and wind them around. So it's actually one single rotor coil that is simply wound around all these slots. That's usually how it is. Now, because of this coil in this manner, if we use the right hand thumb rule, then quite obviously the flux will flow through this rotor all the way and will complete its path through the stator. So for example, I can draw a few such flux lines. So I'm just going to use the free hand, right? May not be very good, but doesn't really matter. So let me start from here. Of course, you can assume any direction, but let's just assume something for now. So let's say this was one flux line, horrible line, but anyway, and let me draw another one. Okay, imagine these lines are actually nice smooth flux lines. As I said, drawing is not my specialty, so this is as good as it gets. So either one, use a better software or try to draw it on your own. But the idea here is, because it's the same concept that whenever current flows through any conductor, the flux will be concentric to the conductor and will encircle the conductor. Right? In this case, of course, there will be some flux lines which also pass in this manner. Right? There will be some flux lines because, as I said, not all flux will associate with the stator. Some flux will just leak into the air. So there will be some flux like this which actually does nothing useful. But on the whole, most of the flux will flow in this direction. Alright, so we can consider that whichever direction. So for example, we can say that the flux were to flow in the counterclockwise direction, and here the flux were to flow in the clockwise direction. You can think of various ways, doesn't really matter. What matters is the direction that it flows through the rotor. So let's say it flows through the rotor starting from here to here, that is from downwards to upwards, right? So again, we can always break this flux path into several different parts. For example, there is a flux path through the rotor, then through the air gap, then through the stator, and through the other air gap again. So again, we see a distinction. There are three parts. There is one high permeability path through the rotor, there is a low permeability path through the air gap, and there is one last low permeability path through the stator. As already said, because the stator and the rotor are high permeability paths, which a permeability of almost 1000 times higher than that of air, quite obviously the reluctance of this entire flux path can be approximated to just this reluctance of the air gap, right? Because these flux paths, even though they are longer, they are 1000 times higher permeability. So therefore, really speaking, the entire flux path is determined by these air gaps here. So the question here again is, we can do exactly the same calculation that we did for the stator, right? We can say that we can determine we can determine the strength of these flux paths using the radius, because as always we say the flux always chooses the path of least reluctance, and the path of least reluctance will be the path where this air gap has the smallest length, and the place where this air gap has the smallest length is through always the radius. Right? So if you draw several radii, you will find that this air gap, or rather the flux through the air gap, will be passing through the radii. Again, there will be some exceptions to this because not all will flow uniformly. Some will, of course, there will be exceptions, but a vast majority of the flux will flow through the radii. So now that we have this, we have now drawn the flux of this rotor in this particular position. The question now arises, what happens when this rotor will rotate? That is the question. Because when this rotor rotates, that's when the rotor position angle changes, and when the rotor position angle changes, that is when, if we determine how the flux changes, we know that the flux is now different with respect to the position of the rotor. So to be able to determine how this rotor will behave when it rotates, I need to select it as an object. So the first thing I'm going to do is I'm going to move these two stator coils because I need to select the rotor. Let me just move it out. And now that we have this, let me select the rotor. So I'm selecting the rotor along with all the flux lines, right? So let me just verify, yes, these two have not been selected. Go to object and I'll group it. So now that I've brought this group in, let me bring this back to the center. These are the stator slots, that doesn't change. And now if I select it, I get the entire rotor. That is, I get the rotor along with the flux lines. The entire thing has been selected. So now, simply speaking, if I do a rotate, I have rotated this rotor by 90 degrees. Of course, you can rotate it by any angle. It's just that I don't think the other angles are very conveniently available. So that's why I do it by 90 degrees. And of course, you can do it as many times as you want. So you can just keep rotating it, right? So now that we rotate it in this new direction, what happens? So let's take a look. Always, when we need to find out what's happening, we must examine how has the flux path changed. That is, if we take this one flux line, which is now in this new position, again we see exactly the same three segments. That is, there is a high permeability segment through the rotor, there is a low permeability segment through the air gap, a high permeability segment through the stator, and another low permeability segment through the air gap. Exactly the same three segments. And once again, we can make the approximation that the high permeability segment through the rotor and the stator can be neglected and consider only the air gap instead. And as you can see, since we are considering only the rotor flux because of the excitation of the rotor, it is very clear that this air gap is not changing. The air gap does not change if I rotate it. This is totally different with respect to the stator flux. Now if I take this stator flux, if I rotate this rotor, you will see that the air gap for the stator flux is changing drastically. Look at the flux here. It is totally different with respect to the flux in this position. Totally different. Whereas here you see that the air gap for the flux has not changed. The reason, because it is a rotor that is producing this flux in the beginning to begin with. So therefore, it is very clear that in the case of a salient pole rotor, the rotor, if the rotor itself is excited, there is no difference to the flux produced by the rotor as the rotor rotates. And if the flux produced by the rotor is independent of the rotor angle, then one can say that the self-inductance of the rotor is also independent of the rotor angle. So it is quite a surprising observation here as compared to here. Here you see that because the stator is excited and the rotor is moving, the stator inductance is dependent on the rotor angle. Whereas here, because the rotor is excited and the rotor is moving, there is no difference, there is no dependence on the rotor inductance on the rotor angle. So therefore, the reason why I wanted to show you this is that sometimes we tend to jump at conclusions, and it is a quick conclusion that you can jump at. You can jump at this conclusion thinking that because it is a salient pole rotor and because the self-inductance is a function of the rotor angle, the rotor inductance should also be a function of the rotor angle. But that's not the case. And this is something which is very clear once you draw the flux path. And you can verify that yourself. You can take a piece of pencil and paper and try to draw it in various different angles, and you will see that the flux path does not change, or rather the length of the air gap does not change, and that automatically means that the flux also does not change. So here, if we were to write a salient pole as well, it would be very different, right? It would mean that if, let me just add, just for the sake of it, add an see, and we can say that for a salient pole, the rotor resistance and the stator, the two resistances, that is the stator resistance, the rotor resistance, and the rotor inductance are independent of theta m for a salient pole rotor, and instead the self-inductance of the stator is dependent on theta m, right? So this case is for a cylindrical rotor, which is the case of a squirrel cage induction motor. Right? This salient pole and rotor is a special construction which is found but is not going to be talked about in the beginning because it's an advanced case, right? So this is something that's worth looking at, and at least when you come to understanding how motors work and how motors behave, in trying to build a mathematical model, these flux lines play a huge role. And this is why I say always when you're trying to understand how a machine behaves, try to draw these flux lines and try to figure this part out, because this is the real understanding of a machine rather than just writing equations. So now that we have completed this, the next lecture we will get back to our squirrel cage induction motor, and we'll talk about how the mutual inductance between the stator and the rotor is dependent on the rotor position angle, and we can also write an equation for how this mutual inductance is dependent on the theta m, right? So all this we will do in the next few lectures, but with this we have more or less decided most of the parameters. There's this one last parameter remaining, and therefore we are fairly close to determining at least a basic mathematical model. The last step, of course, is to figure out how the torque will be produced because of the stator flux and the rotor flux, and this last part of determining the torque will again have us go back to basic physics and understanding how force is produced due to interaction of fluxes. So with this, I'm going to end this lecture. If you have any doubts, please do either comment or send me a message on social media or email me, whichever is your preference. Otherwise, I will see you next week, where we will continue with this last one parameter, which is the mutual inductance. Thank you so much for watching, and see you soon. Goodbye for now.